page 380, we're going to start a section of integration techniques. And it's called inverse trigonometric functions integration. It's a little misleading. We're not going to take the integrals of the inverse trig functions. We're going to take integrals whose answer is an inverse trig function. Okay? And we're going to do it by reversing the derivative formulas that we have. All right? So it says the derivatives of the 6 inverse trigonometric functions fall into 3 pairs. In each pair, the derivative of one function is the negative of the other. For instance, the derivative of arc sine and the derivative of arc cosine are identical except for a negative in front on the arc cosine. Now, when listing the antiderivative that corresponds to each of the inverse trig functions, you need to use only one member from each pair because all you got to do is factor out a negative. So it is conventional to use arc sine of x as the antiderivative of 1 over the square root of 1 minus x squared instead of using negative arc cosine of x. So we took 6 derivative formulas and we're condensing it into 3 integration formulas because there's no reason to have 2 identical ones except for a negative sign. Okay? So here they are. And you're going to have to memorize these. If you have the integral, and you know, I wouldn't write the du up there. I would write them like this. If you have the integral of 1 over the square root of a squared minus u squared, where a is a constant, that equals the arc sine of u over a plus c. Second one, the integral of 1 over a squared plus u squared, where a is a constant, is 1 over a times the arctangent of u over a plus c. And the last one I would have is the integral of 1 over u times the square root of u squared minus a squared equals 1 over a times the arcsecant of the absolute value of u over a plus c. So that's just about as complicated as things can get. Ever? Yeah. For us, that's about as complicated as it's going to get. So, there's our 3 new integral formulas. And in this section, there are, for the problems they expect you to be able to integrate, there are too many variations for me to work you an example of every kind of situation you might face. With derivatives, we can generally narrow it down to do this, this, or this. With integrals, it's might as well be an infinite number of possibilities. There's so many possibilities. So, you must take the time to check out example 1 and 2, 3. Example 4, you are just going to love completing the square. Example 5, you're just going to love completing the square with an expression that's not built to complete the square. And then you run into all these. So, seriously, you've got to read those examples and not read them as in just to say the words to yourself. Study those examples. They have techniques that you're going to have to be able to do. Okay? So you've got to study those examples. Now we've got a bunch of integration formulas. Do we have as many integration formulas as we do derivative formulas? About, but not quite. All right, here's what the book says, and I like this. I'm just going to read it here. You can learn a lot about the nature of integration by comparing this list with the summary of differentiation rules given in the preceding section. For differentiation, you now have rules that allow you to differentiate any elementary function. Some of them aren't all that easy to do, but we have a rule for everything that's an elementary function. For integration, this is far from trivial. The integration rules listed above are primarily those that were happened on when developing differentiation rules. So they're mostly just the derivative rules backward. Okay? So far, you have not learned any rules or techniques for finding the antiderivative of a general product or a quotient, the natural logarithmic function, or any of the inverse trig functions. We can't integrate any of that. More importantly, you cannot apply any of the rules in this list unless you can create the proper du corresponding to the u in the formula. So even if it's something that we think we're supposed to be able to do, if we're not able to make the du work out, we still can't do it. The point is that you need to work more on integration techniques, which you will do in Chapter 8. And my guess is Chapter 8, Chapter 9, Chapter 10, Chapter 11. That's the reason there's 4 semesters of calculus in college. Okay? Not everybody's required to take all 4, but that's the reason 4 semesters of it exist. The next 2 examples should give you a better feeling for the integration problems that you can and cannot do with the techniques and rules you now know. Because it's really frustrating to spend an hour and a half on a problem that we don't know how to work. Isn't it? Or wouldn't it be? Okay? So, on example 6, if you look at this one, A fits the brand new arc-secant rule, so we could do A. B, you can do with the substitution and make it a power rule. And C, even though, look, C looks, if anything, a little less intimidating than A and B. We can't do C. It doesn't fit any of our present techniques. Okay. All right, look at example 7. You can make A work. You can make B work. C looks simpler. Can't do it. Okay? Now, remember too, there's a difference between saying that we can't do it and then saying it can't be done. Because we're beginners at calculus. There's a lot more out there. Okay? But the point is, look, if they tell you for number 7, find the integral, you'll be able to do it, in theory at least. But don't get all cocky and think, I know how to integrate now. You know a little bit about integrating now. Okay? All right, let's do a few examples from your assignment. Let's start with number 10 on page 385. The directions are real simple. Find the integral. And I recopied the new formulas from today so that we can try to figure out which one we want to use. Now, that doesn't mean that every problem in this section is going to involve one of the new formulas. But, most of them are. So we've got the integral of t over t squared, over t to the 4th plus 16 dt. Now, none of our formulas have a t, so we've got to use a little bit of an imagination. Which one of these does this look most like? The arcsine formula, the arcsecant formula, or the arctangent formula? Arctangent. Why do you think it looks the most like arctangent? Not a square root in it. Good enough. Okay? If we're going to make this look like this, all right, let's figure out what's got to be what then. Now, our formula has the constant squared in front plus and then the u squared. This problem has it reversed. Since it's a sum of those two, does that matter? No, not at all. If it was a minus sign between them, yeah, it would matter. Okay? So keeping that in mind, the a squared is our 16. Well, if a squared equals 16, what's a? Okay? And then the u squared is our t to the fourth. If u squared is t to the fourth, what's u? So that's what I'm going to write down first. Let u equal t squared. And then I'm going to let you use your own judgment on whether or not you want to write down what a equals. Okay? Because sometimes if I don't write it down, I'm going to mess it up. Other times, you know, I'm kind of sharp that day. I can keep the fact that a equals 4 in my head for 5 seconds to write it down. Okay? Now, we've got to make sure everything else works out, right? Forget about what the answer is going to be. We've got to make sure we can make a substitution that turns our problem into that formula. Okay? So, if u equals t squared, what's du? 2t dt. Didn't really want the 2, did we? All right, there's no 2t dt. So what do? Yeah. So that'll give us 1/2 du equals t dt. And let's see if we can make the substitution then. All right? So, just think with me for a moment here. Don't worry about writing yet. I'll give you time. We've got the integral of, we've got a fraction. All right, t squared. Or no, in t to the fourth. Instead of t to the fourth, I could call that u squared. So I'm taking care of that. Plus 16. I can leave the 16 written as 16, or I could write it as 4 squared to make it more obvious that it's a squared. Either way, I don't have to substitute anything. Either rewrite the 16 or not. I suggest going ahead and rewriting it. Okay? Now, I've got to replace t dt. Well, t dt is replaced with 1/2 du. Now, if I really want to make it look exactly like the book's version of the formula, I'd put the du right there. Does it fit? It fits. Okay? So, now, write it down. And I don't really care if you put the du in the top or the du at the end like I'm going to keep doing, because that's just the way I do it. But either way, that's our new integral. You with me? All right, everybody had time to write it down? All right, use your formula. Okay? The integral will be 1 over a. What's a? So, don't forget the 1/2 in front. And then 1 over 4 times the arctangent of u over a. So, times the arctangent of u over 4 plus c. Plus c. All right, well, 1/2 times 1/4 is 1/8 times the arctangent of, and instead of u over 4, you need to go back to your original variable. U equals t squared, so make that t squared over 4 plus c. And that's how we do number 10. Make sense? Okay. Even the ones that make sense, you're going to have to be really careful on. Lots of places to goof it up. You got to identify the correct A. You got to identify the correct formula that you're trying to fit, or you won't, you know, I mean, if you're not even trying to fit the right one, you're in trouble. So, still lots of places to goof up. So, be careful. Let's do number 12. We have the integral of 1 over x times the square root of x to the 4th minus 4 dx. Which one does that look the most like? Arcsecant. Why did you choose arcsecant instead of arcsine? Because it's got the something in front of the square root sign, right? Now, does that mean for sure that we're right? No, but that's what I would aim for as well. I'm aiming for arcsecant. Okay. If I'm going to do that, let's look under the square root sign there. There's your a squared that's subtracted, so that's that. So a is going to be 2. And here's your u squared. That's that. So what's u going to be? Let's write that down. We let u equal x squared. Now we've got to figure out what du equals. That's 2x dx. I must say I'm a little disappointed by that. What I wanted it to equal was 1 over x dx is what I wanted it to equal. Okay, that would have been nice, wouldn't it? But it doesn't. How do I make it equal that? All right. Let's go in stages. I need to multiply both sides by 1/2. That'll get rid of the 2, right? If I had an x in the bottom, that'd get rid of that x. But I'd really like for the x to end up in the bottom, so how about an x squared? So 1 over 2x squared du equals 1 over x dx. All right, don't write this down yet. Let's try to make the substitution. So that'd be the integral of. All right, I'll go ahead and put a 1 up there. Under my square root sign there, that x to the 4th, that can be u squared minus 2 squared. The 1 over x dx gets replaced with that. That's no good. I can do a that, but I can't do a that. Can I? But wait. What's that equal? Equals u, doesn't it? All right, so that 1 over 2x squared du, think of that as 1 over 2u, or as 1/2 times 1 over u du. Right. Now we can make our substitution. So the 1 stays a 1. The square root of the x to the 4th is u squared. The minus 4's minus 2 squared. And then the 1 over x dx becomes 1/2, 1 over u, so a u in the denominator, du. That's a relatively complicated substitution. Are you with me? All right. Well, then let's work the thing. So now, it sure looks like it fits the arcsecant formula. All right, the book would have the du up here instead of here, but we have the arcsecant formula. Okay, so keep the 1/2 in front. Then we get 1 over a. Well, we said a is 2, so 1 over 2 times the arcsecant of, times the arcsecant of, the absolute value of u over a over 2 plus c plus c. You good? All right. Well, 1/2 times 1/2 is 1/4 times the arcsecant of. Replace u with x squared. And I don't need absolute value signs around x squared. It can't be negative, can it? Okay? Now, if you leave them, that's fine as well. Okay? But the arcsecant of x squared over 2 plus 6. Okay? Questions on number 12? 18. We have the integral of 4x plus 3 over the square root of 1 minus x squared dx. That didn't really look like any of those to me. I'm going to go ahead and eliminate this one because that one doesn't have a square root sign in it, and our problem does. I think it's arc sine because we haven't worked an arc sine problem yet. I respect your logic. It's an arc sine, but it's not an arc sine yet, because if it is an arc sine, wouldn't u just be x? And in fact, then a would just be 1. And if you let u equal x, you're not getting rid of that with the du, are you? All right. If I have x plus 3 over 7, isn't that the same thing as x over 7 plus 3 over 7? Isn't it? So, 4x plus 3 over the square root of 1 minus x squared is the same thing as 4x over the square root of 1 minus x squared plus 3 over the square root of 1 minus x squared. So, we break our function up into two pieces. So we take the integral of the first piece, dx, plus the integral of the second piece, dx. Okay? Now, the first chunk. This one. Let's concentrate on this one. Then we'll concentrate on the other one. All right? If I again approach this with the arc sine in mind, u would still equal x, right? And I'm still not going to get 4x dx as my du. Well, maybe then I don't need arc sine for this one. Back up the time machine a month, and what would you let u equal? 1 minus x squared. Let's see what happens. So, we'll let u equal 1 minus x squared. And if u equals 1 minus x squared, du is a negative 2x dx. But we don't have a negative 2x dx. We have a positive 4x dx. So we should multiply both sides by negative 2. And then we can rewrite our integral. Okay? We've got the integral of, and in the denominator, instead of that being the square root of 1 minus x squared, it's just the square root of u. So we took care of that. Now we've got to replace the 4x dx. All right? And what does 4x dx get replaced by? Negative 2 du. All right? We good? Okay. Now, the other one. I can make that fit the arc sine, but the 3's in the way. What do I do with the 3? Factor it out in front. And now, not only does it fit the arc sine, I don't even need a substitution, because that u equals x that we kept wanting to do really does work, doesn't it? That is it. Well, if u equals x, du equals dx, there's no need for a substitution. just use x with your formula instead of a u. Okay? All right, so we got to try to do two integrations at once here. Let's do the one on the left. All right? So the one on the left, keep the negative 2 in front. And then the integral of 1 over the square root of u. I'm doing a lot of this in my head. 1 over the square root of u is the same thing as u to the negative 1/2, correct? Power ruler. Add 1 to the exponent, makes it a positive 1/2. Divide your coefficient by that new exponent of positive 1/2. Dividing by positive 1/2 is the same thing as multiplying by 2. Multiply the coefficient by 2, and that's now u to the positive 1/2. I'm not going to bother with the plus c. I'll just put a plus c at the end of the whole thing. Okay? Now, let's take the integral of the rest of this. Well, it's 3. And then the integral of 1 over the square root of 1 squared minus x squared dx is the arc sine of u over a, in this case, x over 1 plus c. Yeah, and the x over 1 I'm going to change to just an x here in a minute. All right, so it's been tough getting here. Are you here with me? All right. Well, if I remember correctly, negative 2 times 2 is negative 4. U to the 1/2 is the same thing as the square root of u. Replace u with 1 minus x squared, so that's the square root of 1 minus x squared plus 3 times the arc sine of x over 1 is just x plus c. Well, that was fun. Debatable. Huh. All right. Questions on 18? You getting the idea you're going to have to use your brain in this section? You getting the idea you're not going to be able to coast through this one? All right. Last example for today, number 20. We have the integral of x minus 2 over x plus 1 quantity squared plus 4. I'm thinking maybe there's an arctangent in there. But, you know, I'm not real certain because I can't go straight from there to there, can I? It's not going to be that simple. So I'm thinking arctangent, but I'm not willing to commit to it. Okay? All right. Well, maybe I need to do what I did last problem and make that x over all that stuff minus 2 over all that stuff, and that'll work out just great. I tried that. I couldn't get it to work. Okay? So I need a different technique. Well, everybody knows that negative 2 is the same thing as 1 minus 3. Don't we? So I rewrote the negative 2 as 1 minus 3. Why not? Why can't I do that? I thought of that. And I had a reason for thinking of that. Because I remember I tried the other thing. I tried breaking it up with the x on the top, with the negative 2 on the top, and I couldn't make it work. Does that help? All right. So what I'm going to do now is I'm going to try that again because, you know, I'm stubborn and I really wanted that technique to work. So I'm going to break it up with the x plus 1 as my numerator for the first term, and the negative 3 as the numerator for the second term. We're not cheating, we're being smart. Thinking is not cheating. Maybe that's been the trouble all along. Thinking is not cheating. Yes. All right. Now, let's look at the one on the left. Okay? You know how we started off thinking that maybe we were going to have an arc tangent in this problem? Not from the one on the left one. Because if you try it, you let q equal x plus 1 and a be 2, you can't get the x plus 1 dx. Okay. No, that's right. Well, let me take it back. Maybe you can get it to work out. I didn't. Right? So, what could we possibly let u equal? What's that? The whole denominator. Let's let u equal x plus 1 quantity squared plus 4. And if that's what u equals, du is going to equal, now, the integral of x plus 1 quantity squared, chain rule. That's u squared, right? Different u, u squared. 2u times the derivative of u. So 2 times x plus 1 times the derivative of x plus 1, which is 1. So 2 times x plus 1. What's the derivative of 4? 0 dx. Okay, well look, that's pretty cool, except for the 2. So we could rewrite this one then. All right, I'll do it up here, then I'll put it in the proper place. All right, our denominator of x plus 1 quantity squared plus 4, all that got replaced with u. Our x plus 1 dx is replaced with 1/2 du. Can't leave a blank space, so put a times 1 in there. That's our new integral. Put the next little blue spot, it kind of looks like a minus sign, but it's just a plus on the skin. So that's not there. It can be multiplication, that's fine. That doesn't hurt. All right, so cool, huh? You want to go ahead and integrate it? Yeah. So 1/2, and then the integral of 1 over u du is the natural log of the absolute value of u. I'll put plus c e. All right. Sure hope we can integrate this second one. Because if not, we just wasted our time. All right, for the second one, if I factor that negative 3 out front, put a 1 there, does it match up with the arc tangent? So we've got the negative 3 out in front. We've got 1 over x plus 1 quantity squared plus dx. What would u equal? Plus 1. That gives us our u squared. I didn't write it down, but what, by the way, I called it v because technically you don't need to have u equaling 2 different things in the same problem. So call it something besides u. So I called it v. All right. I didn't write down what a equals, but what does a equal? 2. All right. So if v equals x plus 1, what's dv? 1 dx. So dx. Now, let's rewrite this to make it fit. So I've got the -3 out in front times the integral 1 over. Okay, so I'm taking care of that, taking care of that. In the denominator, instead of x plus 1 squared, we're going to put v squared. So I'm taking care of that. And you can write plus 4 if you want to. I'm going to write plus 2 squared so that I remind myself a is 2 dv. Keep the -3 out in front. And then according to our formula, right, here's my answer. 1 over a, so 1 over 2 times the arctangent of u over a, which in our case is v over a, v over 2. Now we'll put plus c on there. And it's almost all over but the shell. Yep, let's put our x's back in. So that'll be 1/2 times the natural log of x plus 1 quantity squared plus 4 minus, and then 3 times 1/2 is 3/2 times the arctangent. Instead of v over 2, it'll be x plus 1 over 2 plus c. That's all she wrote. One thing you can do if you want, the x plus 1 quantity squared plus 4 can't be negative. You don't have to have absolute value signs around it. If you don't want to ever risk that, you don't have to risk that. Because if you're wrong, if you have an expression that could be negative, and you take off the absolute value sign, now your answer is wrong. So if you don't want to ever risk it, I'm fine with it. But you don't need them. Okay? Wow, that was fun. Pumpkin. Here's something. They only gave you 52 of them. 1 through 20, 47 through 52.